let us discuss now the following theorem, the Archimedean property of the real numbers of R. This is called Archimedean, crediting Archimedes, because apparently this property appears as an axiom in Archimedes' work on the sphere and the cylinder, as credited by Euclid in his book 5 of the elements. So this goes a long way back, but in this context, it appeared like in the 19th century, okay? When they were putting the real numbers in order. So what does it say? So what the Archimedean property of R says is that if we have two numbers, two real numbers, x and y, and x is positive, observe that they are not saying anything about y. Okay, y could be negative or 0, but x has to be positive. Then there exists a positive integer n, okay, such that nx is bigger than y. So what does this mean? I did here a picture. So you see here we have our number x and our number y. X is positive. I also took y positive and bigger than x just to as an example. And here I just copied the distance from 0 to x, and I copied it several times, 3 times, until I exceeded y. So the Archimedean property is saying that there is a number n, in this case 3, that whatever the number x is and the number y is, you can copy the length from 0 to x a number of times until eventually you exceed y. So you may be wondering what's the big deal here. So here what we are saying is that in R, all the numbers, all the members in R are comparable to each other. Okay, there is no element that is extremely huge or extremely small that has no comparison to the rest. Okay, that's it. Now, you may be wondering, but does that ever happen? Yes. I mean, not in R, but in other structures, yes. So this is a property that R has, but some other structures may not have. So let's get to the proof. By the way, you may have noticed, but here this capital E looking backwards means there exists, okay? So this is an abbreviation for there exists. Now, proof. So this statement has a structure of if-then, right? So looking at this type of a statement, it looks like a proof by contradiction could be a good option. Okay, so let's assume to the contrary. Let's say that this is by contradiction. You want your reader to be informed. So assume to the contrary. That, and then you need to, in the if then, you need to negate the conclusion. So you need to negate the, there exists n in the natural number such that nx is bigger than y. So in this case, we are saying nx bigger than y, so nx less or equal than y for all n in n. Okay, notice here also capital A upside down. This means for all. Okay. All right, so let's see what can we do with this. The idea of this proof is we are going to try to illustrate what we can do with the least upper bound property. Okay, so we are going to try to, you see, because here nx for all n less or equal than y, it's somehow connected with upper bounds, right? What is y actually? With this definition, y is an upper bound. Okay, upper bound for what set? So let's define the set of the numbers in x, okay, such that n is bigger, n is a natural number. Okay. Remember x, this is the positive number that is in the statement. So this is our positive number. Now, looking here, nx less or equal than y, this means y is an upper bound of a, okay, for a. And here, you see what we have been doing so far. We have assumed for contradiction, we have nx less or equal than y, and that looks like an upper bound, but it's an upper bound for the set of nx such that n is a natural number. Okay, and now we would be kind of stuck here until we notice, okay, upper bounds in the reals. So there is the least upper bound property. R has the least upper bound property that we saw last week. So that means, therefore, we can apply the least upper bound property to any set, any subset of R. In particular, we can apply to A. Okay, so A has a least upper bound in R. Okay, so the property says that every set in R has a least upper bound that is also in R. Okay, remember this didn't happen for the rational numbers. Now, what is this least upper bound? Let's call it alpha. This is the supremum of A. Okay, the least upper bound is the supremum of the set. So here let's do a sketch of what's going on. So we have our set A, and here we have our alpha. That is the least upper bound. Okay. So now, let's see what can we do here. Remember, we are aiming for a contradiction, so we need to see what we can do, okay? So clearly, let me write it like this, maybe it's a little more clear. So alpha minus x is less than alpha, right? Because x is positive. So we are subtracting something positive, we get something smaller. Now, where is that alpha minus x is going to be somewhere to the left of alpha, okay? Alpha minus x is not an upper bound for A, okay? Alpha is the smallest. Is the smallest one, okay? All right, and we saw here it's a strict alpha minus x is less than alpha. So what happens Let's go back to our picture. What happens if alpha minus x is not an upper bound for A? Well, it has to be less or equal than some element in A. Otherwise, it would be an upper bound. Okay, does everybody see this? Okay. So then alpha minus x is smaller than some element in A. Let's call it, all the elements in A are of the form, remember, nx. So let's call it mx. M, a natural number. Okay, we are getting somewhere here. So we have alpha minus x less than mx, okay? And then, well, what shall we do here? We have x's on both sides. So we might as well put both on the right? And we have that alpha is less than n plus 1 x. And here we have the contradiction we're looking for. So what is the contradiction? The contradiction is that n plus 1 x, by definition, you see it's a multiple of x. So this is an element of A. Okay, so we are saying that alpha is strictly smaller than an element of A, but alpha was the least upper bound of A. So this inequality is saying that alpha is not an upper bound of A, which is a contradiction with the definition of alpha. Okay, that was the supremum of A. And here we are done with the proof. And we can mark it with a little box like this.